What if faster-than-light travel wasn't just a dream from science fiction, but a theoretical possibility hidden deep within the equations of physics? What if, instead of moving through space, we could bend space-time itself, compressing the distance ahead and expanding it behind, allowing a spacecraft to surf the very fabric of the universe? Welcome to Space-Time Engineering and Warp Metrics, a bold and fascinating frontier at the intersection of relativity, quantum physics, and computational modeling. You're watching the Learning Studio, and in today's episode from our physics playlist, we'll explore how physicists and AI researchers are beginning to study the mathematics of warp drives, space-time manipulation, and metric engineering, concepts that could one day reshape how humanity moves through the cosmos. You can explore the entire physics playlist by clicking the link in the description below. This topic belongs to our section Space, Time, and Advanced Technologies, where we explore how modern computation and theoretical physics merge to imagine the technologies of tomorrow. From Einstein to the Edge, the birth of space-time curvature. Our story begins with Albert Einstein's general theory of relativity. In 1915, Einstein revealed that gravity isn't a force pulling objects together, it's the curvature of space and time caused by mass and energy. Massive objects like stars and planets warp the geometry of space-time, and smaller objects simply follow the curves. In other words, we don't fall because of gravity, we fall because the Earth bends space-time around us. But what if, instead of letting nature shape space-time, we could learn to shape it ourselves? That's the idea behind space-time engineering, the theoretical study of how to manipulate curvature intentionally. The Alcubierre Drive, a warp bubble in space-time. In 1994, Mexican physicist Miguel Alcubierre proposed something astonishing. A solution to Einstein's field equations that, at least mathematically, allowed for faster-than-light travel without breaking the laws of relativity. Instead of moving through space at impossible speeds, the Alcubierre Drive would contract space-time in front of a spacecraft and expand it behind, forming a warp bubble. Inside the bubble, the spacecraft would remain stationary relative to its local space-time, experiencing no acceleration, yet to an outside observer, it would appear to move faster than light. In simple terms, it doesn't break the cosmic speed limit, it changes what distance means. The challenges: exotic matter and negative energy. Of course, there's a catch. To create such a warp bubble, the Alcubierre metric requires something we don't yet have: negative energy density or exotic matter. This isn't ordinary matter, it would have to bend space-time in the opposite direction of normal gravity, essentially creating anti-gravity zones. While quantum field theory allows for negative energy in tiny regions, like the Casimir effect, generating and sustaining it on a usable scale remains far beyond current technology. Still, researchers across the world, including theoretical physicists and computational modelers, are exploring modified warp metrics that reduce energy requirements or use quantum effects to stabilize the geometry. And here's where AI and simulation enter the scene. AI and computational physics, modeling the impossible. Simulating a warp bubble is no trivial task. It involves solving Einstein's field equations, 10 interlinked nonlinear differential equations, in 4-dimensional curved space-time. AI, especially in the form of neural solvers and physics-informed machine learning models, is becoming a crucial partner in this effort. These systems can approximate complex relativistic geometries faster than traditional computation. Explore parameter spaces of warp metrics to identify stable or energy-efficient configurations. Visualize and simulate dynamic curvature in real time, offering new insights into how matter and energy could shape the geometry of space itself. In essence, AI is helping physicists prototype space-time, long before we can physically engineer it. Quantum gravity and the future of space-time design. Space-time engineering doesn't exist in isolation. It touches the deepest open questions in modern physics: quantum gravity, dark energy, and the holographic nature of the universe. The next generation of physicists may not just study the universe, they may learn to design within it. By uniting relativity, quantum field theory, and computational intelligence, humanity could one day master the art of space-time architecture, guiding how we move, communicate, and even exist across cosmic distances. While a real warp drive may still be centuries away, the mathematics we develop today may become the foundation for the first true engineering of the universe itself. Why it matters. Space-time engineering is more than a scientific curiosity, it's a reminder of how physics turns imagination into mathematics, and mathematics into potential reality. Every breakthrough in relativity, quantum mechanics, or AI-driven modeling brings us one step closer to understanding, and perhaps harnessing, the most fundamental structure in existence, space-time itself. It's not just about traveling faster. It's about learning how to shape reality, responsibly, intelligently, and in harmony with the universe's deepest laws. This is the Learning Studio, and this was our episode on space-time engineering and warp metrics. If you enjoyed exploring how theoretical physics and computation might someday let us navigate the fabric of reality, make sure to like, subscribe, and check out our physics playlist linked below. In our next episode, we'll venture into cosmological simulations and digital universes, where scientists are recreating the cosmos itself inside supercomputers. Because in physics, what begins as theory often becomes the blueprint for tomorrow's reality.